Okay, we are going to do 6 through 10, I think is what the plan is. Find the sum of the measures of a 12-sided polygon. So you might remember we came up with this formula for it, the formula to find the sum of the measures of the interior. I probably should have said that, of the interior angles. Yeah, they didn't say that. I didn't say that. So it's 180 times n minus 2 is the sum. So let's plug in. N is the number of sides. So we have 180 times 12 minus 2. PEMDAS says do parentheses first. Oops. Times 10 is 1,800 degrees. So we're talking about angles. I feel like that question is missing a lot, but there it is. 1,800 degrees. All the angles add up to that. Find all of the variables. We have really 3 problems in one here, but we have a right triangle and we have an angle and a side. If you have just 2 pieces of information like angle, side, and a right triangle, then it's a SOHCAHTOA problem. SOHCAHTOA. You could use that to help us set things up. So let's find y first, just because. This is our reference angle because that's the one they gave us. The 90-degree angle can never be the reference angle. Going straight across, that's opposite. The information they gave us is opposite. We're looking for y. That's right next to, we call that adjacent. Looking up at SOHCAHTOA, we have an A and an O, and the only one that has an A and an O is the TOA part, which is tangent. So that tells us we're going to use the trig function tangent. To set up a trigonomic equation, it goes trig function times the angle, 24.6 degrees, is equal to the ratio. The ratio is, in SOHCAHTOA, we can see it is opposite over adjacent. So opposite was 16, adjacent was our variable we're looking for. And I told you to always multiply by the denominator first. And that's fine. It's a little bit not helpful yet because we don't get the variable by itself. And of course, that's the goal. The y's become a 1, which you might say cancel out. But we're trying to get the variable by itself. We don't have it by itself. Now the variable is being multiplied by this tangent 24.6. So to undo that or get rid of it, we can divide it because it was being multiplied. But we have to do that on both sides. These become a 1 or cancel out, giving us a y equals, I'm going to run out of room, I can tell already, 16 over tangent of 24.6. That's the exact answer. We go to our calculator to get the estimate. I can't see it. So we go 16 divided by tangent. Wait, time out. What do I have to do first? Check the mode. Make sure your calculator is in degrees. It is. If it wasn't, we would arrow down, arrow over, hit enter. Quit that screen. Now we go 16 divide tangent of 24.6. Yeah. Enter, and we get 34.95. The 7 makes us round this up by 1. 34.95 is the estimate. About 34.95 units, whatever it is, we don't know. It's a side length. It's not degrees because it's not an angle. Boy, am I going to run out of space. Okay, let's do it again. Let's look for z this time. We still have the same reference angle. We still have 16, which is opposite. I could use, this is now 34.95. I could use that. It's not a good idea because that's not an exact answer. And if I use an estimate in my work to find another answer, then the answer is even farther from accurate. So you're better off using given or better exact numbers. So here we go. We have opposite. This time I'm looking for z, and that is the hypotenuse. The only one that has O and H is SO, or sine is the trig function. Give myself some room. So we're going to set it up sine. Always the angle after the trig function equals the ratio. The ratio is opposite. It tells us opposite over hypotenuse. Opposite on top, hypotenuse on the bottom. Just like the last one, our variable was down below. So yeah, we could multiply by z, and then in the end, we're going to end up dividing, just like the last one. So let's jump right to it. Z is going to be 16 over sine of 24.6. And we'll put that in the calculator to get an estimate. Oops, ran right off the board. All right, here we go. So we have 16 divided by sine of 24.6, and we get an estimate of 38.44 when we round it. Okay, we have exact and estimates there, but I think they're going to ask you for the estimate, but you should know both. All right, one more variable, x. We could use something called inverse trigonometry, which we didn't cover. It's totally not necessary because you've got two angles. You need the third one. You have 24.6. Don't forget we have a 90-degree angle here. So it's as simple as 24.6 plus 90, that's a plus the unknown. All triangles, angles add up to 180 degrees. That's called triangle sum theorem. And we'll go 24.6 plus 90. Let's see, 4. There we go. Plus x is 180. Subtract the 114.6. And we get our x value. I'll just go straight calculator here. And 180 is, oops, that's not it, 114.6. And I get 65.4. 65.4. This is degrees because it is an angle. All right. Moving along. I'm going quickly because you can pause and fast forward and rewind and all of that fun stuff. A pole casts a 10-foot shadow. We're going to want a diagram here. We've got a pole, it's on the ground, probably straight up and down. Somewhere off in the sky is the sun creating a shadow. The shadow is down here. And that's where the shadow ends, where the sun's creating, I don't know what I'm trying to say. It's a 10, I'm just rambling. It's a 10-foot shadow. Sally is 5 feet tall. There's Sally right here. She's standing straight up and down, hopefully. And she is 5 feet tall. And she creates a shadow. My my diagram isn't going to be perfect. She creates, does not look right. Looks like an N. It's an FT for feet. It really looks like an A. Anyway, I'm trying to fix it. It's feet, 5 feet. She creates a shadow that is 2 feet. And what we have here is because the sun is creating this pathway here, this angle has to be the same as that one because it's the same time of day where this all happened, the event happened. And assuming they're both straight up and down, we have two angles that are the same in these two triangles I created. If two angles are the same, that's enough to say those are similar figures. When we have similar figures, we can set up a proportion problem. I didn't even read the question. It says, how tall is the pole? That's our unknown. So we can set up a proportion problem. The way we've set it up is we've had the same triangles information in the numerator, the same triangles information in the denominator, and corresponding parts within each fraction. So if I have 5 and 2 in the same triangle, I can put them anywhere I want. But if I put 5 in the numerator, I have to put 2 in the numerator of the other fraction. What corresponds to 5 is the x. It's in the same spot. What corresponds to 2 is 10. And again, the x and 10 are in the same figure. We've got our proportion set up. Cross multiply. We get 2x is equal to 50. And divide by 2, and x is 25 feet. The pole is 25 feet tall. All right, this is one we didn't cover. I must have misunderstood my team. Thought we weren't going over proofs. This is called a proof. A proof is like you're a lawyer in a courtroom and you're trying to prove something. And a lawyer in a courtroom spends a lot of time providing evidence with every statement they make to make the jury believe what they're saying is true. And the same is true in math. If I'm trying to prove this, the truth is this is a really bad proof because it could have been done in 2 steps, but I'm going to do it lengthy just to show you how proofs work. But every statement we make, we have to say, how do I know that's true? I didn't label these either, right? That's A and that's B. So line A and B are parallel. Well, that was just here given to me. They told me that that was true. It's like telling you the sky's blue. I'm saying that that's true. You're going to believe it. It's given. That's the reason I know it's true. It was given information. The next statement is 2 is equal to 3. So I don't want to mark this up too much, but I'll start by marking. How do I know? What mathematical evidence do I have that I know that those 2 angles are equal? And the answer is they are vertical angles. That's my justification. That's how I know. I can't just say it's true. I have to tell you why I know it's true. And then 3 and 6 are also equal. This one's equal to that one. How do I know that's true? What mathematical proof do I have that those are true? You might remember 3 is on the left, 6 is on the right of the transversal. They're on opposite sides of the transversal. They're also both inside the parallel lines, so we call that alternate interior angles. And we know that alternate interior angles are equal if the lines are parallel. Like, I couldn't have said this statement was true if I hadn't already said those are parallel. It's only true if they're parallel. So it's like very important that I mention that those are parallel. All right, 6 is equal to 7. Again, that's vertical angles. Oops. And 2 is equal to 6. Okay, 2 and 6, how do I know that's true? Those are in the same spot. If I just look at that intersection and that intersection, 2 is in like kind of the top right corner, you could say. 6 is also in the top right corner. When they're in the same spot, we say they're corresponding. And corresponding angles are only equal if the lines are parallel. So it's a really good thing I made this statement, or the jury is not going to believe me. And lastly, how is 2 equal to 7? I wanted to say substitution because if, all of these things, 2 to 3, 3 to 6, 6 to 7, and then we finally get to 2 to 6, they're all equal. I could say by substitution, but really, the reason I said earlier is kind of a dumb proof. I could have done without all of those. And I could have just said we had parallel lines, and now I'm ready to prove my final statement. 2 is equal to 7. It's a hard one for a lot of students. 2 is on the right side of the transversal, 7 on the left. 2 is outside of the parallel lines, and so is 7. We call that exterior. So those are alternate exterior angles. And again, alternate exterior angles are only equal if the lines are parallel. So the fact is, I didn't need any of these statements to make my case to prove it, but I was kind of just showing you how we make a statement, we justify, make a statement, justify. It was not necessary though. Moving on. On the final, you'll have a multiple choice problem with proofs, and it'll all be filled in except maybe one. And you have to say, what is the justification for whatever their statement is? You'll get it. Not too hard. Factor the polynomial. Wrong direction. So factoring. No, I'm thinking of a different problem. Anytime you have an expression, a polynomial, you want to look for common factors. Like when we have quadratics, we know several ways of factoring, but the first thing you should always do is look for a common factor, whether it's 2 terms, 3 terms, 4 terms, whatever. And we've got 3 terms here, and clearly they all have an x in them. So there's no question I can factor out an x because they all have one to pull out. So you might again think of this as dividing out. It's really factoring out. But we're going to take out an x from each of those terms. Also, when I look at 5, 25, and 10, my mind thinks of the number 5 because 5 is a factor of 5. It's a factor of 25 and a factor of 10. It's a common factor for all 3. And lastly, if the leading term is negative, it's a good idea to factor out the negative. So we're going to take out a negative 5 from each of these and an x. We're going to factor it out. When I factor out here, those are going to go away. Those are going to go away. They become a 1. Negative 5 over negative 5 is 1. And 1x here will take away one of these, leaving me with 2. So I'm left here with an x squared. Now, when I divide, if I'm thinking of this division, if I divide a negative by a negative, I'm going to end up with a positive. And 5 goes into 25 5 times. One of these x is going to take away one of those, leaving me with 1x. And when I divide here, the negative and the positive, I end up with a negative. And 5 into 10 twice, and these two x's become a 1 or disappear, you could say. Now, it's not a bad idea to see if this part factors, because we may not be done. Does it? We got to check, because we got to factor all the way. We put negative 2 up here, 5 down there. What two numbers multiply to get negative 2 and add up to 5? Oops, can't see that. What two numbers work? There aren't any. You can't multiply to get negative 2 and add up to 5. The only possibilities would be negative 2 and 1, or 2 and negative 1, and those don't add up to 5. So it does not factor any further. So we're done. I should also mention, this is a multiple choice test. A good test taking strategy is if you're totally lost, oh my gosh, I don't remember how to factor, you're going to have 4 answers that look something like this. You could work backwards, right? You could take your answers, take this term out here and distribute it in, multiply it out, and see if you get this question they're asking. So one of those 4 has to multiply to get back to this. So you could do it that way. Good test taking strategies. That's it. 6 through 10 done. Time. Look out for another video. Have a great day.